thanks so much for the organizers for putting this together. And yes, this is really my official job title. So I dare you to classify me as an astro person or a particle person. All right, so why we're all here is we want to know, no, all right, that's okay. We all want to know something about the dark matter, and here is a kind of an overview, broad overview of some of the possible masses. And
hang on a second, let me make that bigger, because that is small.
Yeah, we're having this issue where it looks normal on Zoom. Yeah, it looks normal on Zoom, but somehow. Anyway, right. We've heard already some allusions to this lower mass bound over here. Whoa, uh-oh.
Oh no, it's even smaller.
I don't know what's happened. Maybe I won't touch this anymore. Wow.
It truly is actually.
Gosh.
Hey, principal.
Whoa.
I think the pointer goes out of bounds that
Really? Now you.
All right, I'm just gonna not use this pointer anymore. I don't want to jinx it. Okay. Maybe this is an indication that I'm a theorist, not that I'm a particle person, because I can't figure out how this basic technology works. Right. So we've already heard. Oh no. If I just come over here, can people see this a little bit better?
That's actually.
Because this is the normal size, so I don't know why. Yeah.
I am sorry.
I'm sorry.
Oh, I'm certain this is not your fault. Is there any way you could point to the Canadian flag?
Yeah. Or this board eraser, maybe? I don't know.
Did you need a pointer?
Yes.
No, don't touch it. Don't touch it, because that somehow it messes things up.
It makes the slide smaller and
No,
smaller.
her slides were originally small. That's why I see it up.
Something is. It's okay. It's okay. We're gonna improvise this. Amazing. A stick. Analog. Thank you. All right. So we've already heard about this low mass range and the caveats that it's subject to. So of course, Kier has these very nice bound coming from the Lyman alpha forest, but this is subject to the caveat that this is non-interacting dark matter. And I'm just going to come over here. Oh gosh, but then how will I advance my slides? All right, here's what I'm going to do. All right, I'm coming over. No, now I'm looped in here. God, this is just a disaster. All right. Okay. So caveats, but I want to come over here because there's a lot of hating on WIMPs that goes on, and thank you, Renee. I don't think it's really warranted, but I want to review basically very quickly what is the status of searches for WIMPs, and that's going to kind of be a foil to what I'm going to talk about for the rest of my talk. All right, so many people I think know this, so I'm going to review it a little bit quickly, but WIMPs are kind of the poster child of this mechanism for setting the abundance of dark matter called thermal freeze-out. And this is a very nice thermal history, because all you have to assume is that at some point in the early universe, dark matter was in thermal equilibrium with the standard model bath. That's all you have to assume. So, you know, Anna Karenina, there's only one way to be thermal. Every thermal distribution is alike, right? So that's beautiful. We don't care about what happened before. We don't care about the initial conditions. You end up having a constant co-moving density at early times until the mass is bigger than the temperature. So as the universe cools, you become Boltzmann suppressed. You start riding this curve down while these kinds of processes over here are active. Okay, but this behavior over here cannot persist forever, because as you annihilate away more and more of these particles, and as the universe expands, it just becomes harder and harder for them to find each other and annihilate. So at some point, this process becomes really inefficient. And once that happens, you can no longer change your co-moving density in an appreciable way, and you freeze out. And it just so happens that if you plug in a weak scale mass and a weak scale cross section, you get the observed relic abundance of dark matter for free. And so that is this WIMP miracle, and that has motivated so many of these experimental searches. For example, the ones shown here, showing searches for dark matter scattering on atomic nuclei.
I think it works.
Oh my God.
You are here.
All right. I'll be here all week.
You used to speak though.
All right, Katelin Schutz Comedy Hour. Okay, so this is a model-dependent thing, something I want to emphasize here. So even though we've excluded all of this parameter space and we're going to go all the way down here, the bad news is that this is very model-dependent. So how you equate scattering on standard model nuclei is model-dependent. It's not the same as the annihilation process that sets the relic abundance in the early universe. So WIMPs could be living down here, classic example being a pure Higgsino, and we wouldn't have seen it yet. Okay, so sometimes people say WIMPs are ruled out, but Rebecca Lean and folks wrote this paper a few years ago called GeV scale thermal WIMPs, not even slightly dead. I think the editor made them change the title of this paper, but here they were just making the point that, well, if you want to do it in a more apples to apples way, where you have the annihilation cross-section that is responsible for setting the relic abundance in the early universe, and if that's the thing that you're looking for, then there's actually this whole window that is allowed, okay? So notably down here, you know, your cross sections are too small, so you don't ride that Boltzmann curve down far enough. Up here, your Boltzmann, you ride down the Boltzmann too far, and you get not enough dark matter. And these limits at low masses are driven primarily by things like the Fermi Gamma Ray Space Telescope, where you can have these visible byproducts, standard model states, which can cascade and be observed in gamma rays. Or, more interestingly, for the purposes of this talk, you have these low mass bounds that are driven by the CMB constraint. So let me unpack what that constraint is coming from just a little bit. So here is how I like to think about the CMB. You know, we're looking back away from us, back in time, and we can't really see inside of this plasma that's beyond the surface of last scattering. Okay, so your light is kind of bouncing around inside of this plasma until the surface of last scattering when recombination happens. And then we think of, you know, to leading order, we think of the photons then, you know, free streaming towards our telescopes. It's not exactly true, okay, because of reionization, but, you know, cartoon picture level, it is true. But now what can happen is that if you have a really small amount of energy injection relative to the abundance of dark matter, you can now potentially ionize some fraction of these neutral atoms after recombination. So it's an amazing fact that if you just were to convert 1 part in a billion of the mass in dark matter in our universe, and you were to convert that into radiation through something like annihilation, that would be enough to ionize every single atom in the universe. Okay, so it's a really, really sensitive probe for that reason. And so you end up rescattering these CMB photons, which ends up smearing out the CMB anisotropies in a characteristic way. You can look for it and you can exclude it. Okay, so you can also use things like spectral distortions as a kind of a calorimeter. Okay, you can use Big Bang nucleosynthesis. So if you start injecting a lot of energy during the epochs that are relevant to BBN, you can also mess up this nice flow chart of nuclear reactions. So just suffice it to say that the upshot of all of this is that you can treat the universe like a calorimeter. There's all these different ways that we're sensitive to energy injections. And that tells us that dark matter cannot be a WIMP below around a mass of 10 GeV. There's an asterisk here, unless annihilation is strongly velocity dependent, which I will come back to in just a moment. Now, I was also asked to talk about dark sectors. So I want to just quickly talk about motivating dark sectors and something called the Lee-Weinberg bound, okay, which is a really fun example of just doing some dimensional analysis. So if you look at dark matter masses above the mass scale of their whatever is mediating the force, okay, so if that's like the only mass scale that's relevant in your problem, then you can construct a cross section. Oh, this should be squared. Sorry, there's a typo here. Bad prof, bad dimensional analysis. Anyway, that's a typo. So, right, cross sections have dimension -2. Okay, so you get an alpha squared because you know something about particle physics and you know that you have some number of vertices giving you some couplings. And then this is just coming, there should be a squared here, but it's just coming from dimensional analysis. Okay, but now if you go below the mediator mass scale, now you potentially have more than one relevant mass scale in your problem. And if you know something about particle physics, you know that there's going to be some maybe propagator over here. So you've got to stick the mass of your mediator down here to the 4th power. Okay, and that means that to make this all dimensionally correct, you got to stick the mass of your dark matter particle upstairs. It's got to be squared. So if you have a cross section that takes this kind of form, you can just plug in the numbers. You actually will have to violate perturbativity. So you have to have alpha bigger than 1 if you want to have masses below a GeV that still give you the observed amount of dark matter that we see in our universe. Okay, so and that's true if the mediator is literally a W or a Z boson. Okay, so we don't want to violate perturbativity. So what do? If we go to these low masses, well, we say, well, maybe the mass of this mediator is not set by the mass of the W or Z boson. Maybe it's some kind of new mediator, which allows me to still have something like thermal freeze out. And so for that reason, people usually associate sub-GeV thermal dark matter with dark sectors, where you have this new mediator. So here's kind of how I like to think about the situation. We've seen a number of different Venn diagrams today. So we have over here the standard model, kind of organized by what different forces the matter fields are interacting with. And over here, we might have some new force carrier. Maybe that force carrier has some overlap with other bubbles on the Venn diagram. And maybe there's, similar to the situation over here where you have all these different matter fields, you may also have something similar happening where you may have different matter fields that interact via this new force. Okay. And so that is why, coming back to this diagram, that is why, due to this Lee-Weinberg bound, that is why this mass range over here is often associated with dark sectors. And so the question is, how can we preserve the success of the thermal freeze-out story for these lighter particles? Okay, because I just told you that, well, independently of the Lee-Weinberg bound, we have these issues with the CMB, that we don't want to mess up CMB anisotropies or any of the other probes that we have of energy injection. So how do we do this? And everyone's favorite way of doing this is with something called pseudo-Dirac dark matter. So that's the Dirac-ish part of my title. And so basically what you do here is you say, well, maybe, I have some, maybe some at high energy scales, it's some Dirac fermion and it's charged under a dark U1. So it's maybe talking to something kind of like a photon, but it's the dark version of that. And you can get a sort of splitting between the mass states at low energies if you have some kind of symmetry breaking in your dark sector. So you get a Majorana mass term that splits the two dark matter states. And so you have these two chi1 and chi2 with this mass splitting delta over here. Okay. These Majorana states don't carry a conserved charge. And so the couplings here are off diagonal. And that means that if you want to write down what are your vertices, then your dark photon only has vertices that couple to chi2 and chi1. There's some caveats to that. If you make the left-handed and right-handed Yukawas different, but I don't want to go into that. Okay. So this is a really, really popular model. It's actually pretty wild for me to be giving this talk where Neil Weiner's in the audience, because he's one of the OGs of this model. And just to point to a specific example, one of the papers invoking this kind of model has around 2,000 citations. And in general, people really love to talk about this model in the context of when there are anomalies. So I believe, correct me if I'm wrong, Neil, but this was originally kind of something that came up in the context of this Dama Libra anomaly. Okay, so that got you order 1,000 citations. Good job. Then there was this nice follow-up a few years later, because there was this rising positron fraction, which seemed pretty weird at the time. And so that they wrote this paper invoking the same model that got them 2,000 citations. Good job. There was also recently this xenon 1 ton excess, but this is a photo that I actually took. It was very exciting 2 years ago at IDM when they first sort of unblinded their new results and showed that there actually is no excess, so the excess went away. But for a while there, we were all pretty excited. And in that short time, these papers each racked up around 100 citations, and again, invoking this model. And why we love this model so much? Well, I'm going to take a nice plot from Gordon's work. The thing about this model and the thermal history of this model, and it can evade the CMB constraint for the following reason, is that, so at early times, you kind of have whatever processes like over here that are setting your relic abundance, that are giving you your freeze out. So your chi1 and your chi2 annihilate to give you standard model states like electrons. Okay. Then eventually processes like this are going to be converting, okay, between chi1s and chi2s through scattering off of electrons. But crucially, the thing that, and this is causing these two sectors to be chemically decoupled, or sorry, kinetically decoupled, kinetically coupled. So you have processes like this that are active, they have the same temperature, but eventually that falls out of equilibrium as well. And if your Chi2 is sufficiently heavy compared to your Chi1, such that this mass splitting over here, delta, it's bigger than this temperature of the dark matter, then you're going to be Boltzmann suppressed. Okay, so at the end of this whole thermal history, you have a really small amount remaining of your excited state because it's been thermally depleted through these kinds of processes down here. Okay, so what that means then is that by the time recombination happens, you don't really have your excited state anymore. And so processes over here where you have your excited state and your ground state annihilating to give you standard model particles, that can't happen because your excited state just simply isn't hanging around anymore. It's been depleted. And so for that reason, this is a really popular model to consider for sub-GeV. So, but now with that in mind, the question is, has this parameter space for this well-studied model been mapped systematically, and have all the observables been treated in a holistic way? And I'm going to argue that the answer is no. So the plan for the rest of the talk is just to talk about a few examples of this, basically highlighting the work of these folks over here, including Stephanie, who's in the audience. And I'm going to talk about kind of three different related stories. Okay, try to stay on time here, considering the little issues we had at the beginning. So let me first tell you about resonant inelastic dark matter. So the story I just told you, where you have this e to the minus delta over t, depleting your excited state. Is it possible to have something where you can still be okay with the CMB bounds, but not have a mass splitting that's bigger than the temperature? So is that possible? And the answer turns out to be yes. Okay, so basically, if the mediator is resonant, okay, so what I mean by that, if its mass is very close to twice the mass of the dark matter, then you can basically produce most of your dark matter during like a very, very narrow window in time. And that shuts off annihilations at late times. So again, just to kind of come back to this picture over here, right? If you don't have this nice suppression, if your abundance is really, really high throughout the entire thermal history, so let's say your excited state abundance is really high, then you basically need something to shut off the cross-section at late times. And that's precisely what these kinds of resonances can actually do. So here's a plot from an earlier work by Sania, really excellent postdoc working in my group. And here just is showing the cross-section as a function of 1 over temperature. So you can think of this as being the time axis. And you can see that if you get these resonances in the cross-section, then during kind of the time when you need to annihilate and deplete your dark matter abundance, you're able to do that. But then at late times, your cross-section is really, really low. So even if you have a lot of your excited state still hanging around, this turns out to actually be fine. Now, one thing I want to also mention is that this is something that you can't just arbitrarily fine-tune. Okay, so actually this is one parameter point showing where this would actually be ruled out. Okay, so it's a little hard to read on this plot. Maybe it's easier to see over there. But what these different lines correspond to is different degrees to which you are close to the resonance. And the line that's up here is the line where it's really, really close to the resonance. So how far you are from resonance is less than 1%. And what happens in that case is that your cross-section at late times is actually still too high. And so there are CMB bounds that are actually going to rule out this parameter space. So you're not allowed to be arbitrarily close to the resonance. There's kind of a natural window there to then explore, and then there's a natural stopping point, which is great. So if you're in this kind of resonant scenario, what does the parameter space look like? It turns out that it actually looks something like this. So here, the y-axis, I'm showing the coupling of your dark photon to your regular photon, which determines how your dark photon couples to regular matter. And on the x-axis, I'm showing how strongly the dark matter couples to the dark photon. And you have this kind of funny behavior where basically it seems like in some parts of parameter space, only one of these two parameters actually matters. And indeed, that's because depending on which of these two steps is the sort of rate limiting bottleneck step of your interaction, that is kind of what determines which of these couplings matter. So because this A prime is actually on shell, because this is a resonant interaction, it actually makes it into like a two-step process. Okay, so that's kind of why it has this funny shape. And now you're not allowed to just be everywhere in that parameter space. Okay, so some of these lines, some of these parts of this parameter space are going to be ruled out by the CMB. So you're still going to have this issue where, because you still have this high abundance of excited state particles at late times, if you make certain cross sections too high, then you're going to run into an issue. Okay, so these edges of the parameter space are ruled out, but this region over here is still fine. And this is for a particular choice of mass. And again, this epsilon, as a reminder, is how close are you to the resonance? So you can then ask the question, well, what happens if I change? How close are you to the resonance? And what that does is it kind of sets for you this natural window. Again, this epsilon r of 0.001 is probably ruled out. Okay, so you probably shouldn't take this line so seriously, but there's kind of just this natural window right here. Okay, and there's a natural stopping point. And then you can basically repeat this exercise, but for different masses. I think it's easier to see over there. So maybe I would focus your attention over there.
Why is 0.01?
Yeah, sorry. The dotted parts are ruled out by the CMB. Sorry, I went a little fast. This has to do with this plot over here, where for the couplings that you need to set the relic abundance of dark matter, like those couplings and with that exact resonance and like how close you are to the resonance, it's a very narrow window of time where you're actually on the resonance. And so your couplings are a little bit bigger. And so that means that at late times, your cross section is too high. And so you're still going to face this issue with, in this case, it's the CMB. In principle, there can also be a BBN issue. Yeah. So yeah, if you also start shifting your resonance to be closer and closer to on resonance, you also shift where this like bump is and like at what point in time the annihilation is happening. And so you can also start to run into this BBN issue. Yeah, it's, well, there's, that one is kind of an issue, and there's also this one. So there's kind of both of them.
Right, but the dotted lines with the CMB.
The dotted lines are CMB specific in this other plot. That's these dashed parts of the parameter space. That's right. So if you come too close to this edge over here, you're going to start to be ruled out. Yeah, the point is just that you can't arbitrarily fine tune it. This is like a really nice example where, like, because people, I feel like astro people are always like, oh, you particle people, you're just going to tune this and evade the constraints. But in this case, no, you can't just do that. Okay, so you kind of have this nice finite sized chunk, which is great. Was there a question, Neil? Okay, we'll talk more. Okay. So one thing I want to emphasize is this is really different parameter space. This is a really different target from the usual sort of thermal freeze out scenario. Those cross sections kind of live here. So that's a very, very different parameter space. In the interest of time, I'm going to go a little quick through this next bit, but please feel free to ask me at coffee because I want to get to the goods, which is the simulation stuff. But this scenario also doesn't have the usual thermal history. The couplings, because you're on resonance, can be so tiny that you actually fall out of thermal equilibrium before you're done annihilating. And so you have to like solve this horrible fully coupled system of Boltzmann equations, which my student Nirmalo solved and was very, very patient with. And if you want to capture the full behavior of dark matter, this can actually really make a difference. Coming back to this plot over here, that's like why this isn't straight. It's because of this bending is because of the fact that it's not thermal. So it can affect things by like kind of an order of magnitude in terms of the couplings. You've got these great collider bounds. Again, with this audience, I'm just going to say it's a nice thing because your collider things are coming from above, but your dashed lines are ruled out by the CMB. So there's this nice, like, you know, your collider experiments come from above, your CMB comes from below. So there's like a nice little window there. And this is going to be even more so in the future. I'm going to just go really quickly. You can do direct detection. I don't want to spend too much time on this. You can do indirect detection. Interestingly, so far, this candidate would not have been visible in direct detection or in indirect detection experiments, but not necessarily for much longer because there are these really nice proposals. Okay, but again, I want to get to the goods. So for the purposes of this audience, it's very sad that there's probably little to no structure formation effects, and also probably maybe there could be some SIDM effects. So the vanilla answer is no, there aren't SIDM effects, but downscattering gets a phase space enhancement. So if you have this like abundance of excited state particles kind of hanging around and it's cosmologically long-lived, then maybe you can downscatter and do something interesting. I'll come back to that in a few minutes in my talk, okay? But let me tell you really quickly about this other mechanism, which is thermal-ish, called freeze-in, where you basically just take this time arrow from freeze out and you pretty much just flip it around. Okay, so now instead of having dark matter annihilating and giving you standard model particles, you have the standard model particles annihilating and giving you dark matter. And unlike this case where the dark matter is in thermal equilibrium, this dark matter cannot be in thermal equilibrium. If it were in thermal equilibrium, we would just get freeze out all over again. That's the beautiful thing about freeze out, Anna Karenina, right? So some other nice features of freeze-in that are kind of relevant here is that, so this is kind of a natural stopping point, I would say, also in terms of thinking about dark matter that's thermal or thermal-ish, because this kind of represents the smallest meaningful dark matter contact with the standard model plasma. So it's kind of like a really natural, again, kind of bookend point for dark matter searches. And in the context of this pseudo-Dirac dark matter, you can have the same kind of process, like two fermions annihilate and give you your dark matter particles. Again, it's just the flipped diagram of what it was for the freeze out case. And so you can go and compute what the couplings are. They're really, really tiny. And you can also show that the ground and excited states are produced symmetrically and they stay more or less symmetrical, okay? So again, in the interest of time, I'm gonna just very briefly say that there's great complementarity with collider probes, but that's not what this audience cares so much about. What we care more about is the cosmology. So what is happening in this situation with the excited state? And is it hanging around and being long-lived? So it kind of depends. So in the parameter space that we looked at for this model, the lifetime, it's 10 to the 7 seconds, so around a year, so not very cosmologically long-lived. But it has a very steep scaling with the mass of the mediator and the mass splitting. So it's to the 4th power and to the 5th power. So there's a possibility for this lifetime to span a really enormous range without changing your parameters too much of your theory. So you can be in a situation where this state is maybe hanging around for hundreds of thousands of years or maybe even longer. And basically what happens is that most of the mass splitting energy goes into something like recoiling electrons when it does decay. And also your ground state over here can get like a little velocity kick. Okay, so that's kind of an interesting different cosmology from cold dark matter, from what we're used to. And one thing I'll just mention in passing is that these kinds of decaying dark matter scenarios have been really interesting for people due to like interest in the Hubble tension. But I would say a lot of those models are a little bit ad hoc. Whereas in this scenario, the couplings that are responsible for setting this decay lifetime are the same couplings that are setting the relic abundance of dark matter. So there's a very one-to-one nice correspondence there, okay? So coming back to what I said in the earlier parts of my talk, you can kind of, actually, maybe let me go back. You can follow what happens to these two electrons and what effect they actually have on the subsequent evolution of the universe and seeing what kinds of energy that they inject. And you can show basically that large swatches of the parameter space are ruled out by things like I was saying about Planck and looking at CMB anisotropies, spectral distortions, BBN. So here I'm showing for 3 different dark matter masses. You end up with windows of parameter space here when the lifetimes are very, very long, or like over here where you have shorter lifetimes, so before kind of the spectral distortion window. Okay, so that's kind of like one signature that you can look at, but perhaps of more interest to this audience is knowing what happens from the velocity kick. Okay, so we wrote this nice white paper. This axis is wrong. I should have updated this plot, but that's fine. But basically showing that we have all these great probes of structure formation. We can use them to try to see if when we kick the ground state particle that we make, can we maybe like smooth out fluctuations in the universe because we're giving a velocity kick that's making it harder and harder for these things to cluster, in analogy to warm dark matter. So we didn't actually do this in detail. I have currently a really talented master's student who's working on this in detail. What we did for our paper was just to compute the free streaming length of this kicked ground state, and to equate that with the free streaming length of the equivalent warm dark matter candidate that has been ruled out by a number of different probes, and then just draw a line there just to make an estimate. So these are just estimates, but we do think that based on these estimates, like present day limits, if you take some of the more aggressive ones on warm dark matter, can maybe start to eat into some corners of this parameter space. And if you go into maybe the Rubin Observatory, or if you start thinking really far future, you can look at different parts of the parameter space as well. I know I'm like out of time now, but I had some technical problems, so maybe grant me like a couple more minutes if that's okay with the organizers. All right, so I want to now come to this question, well, what if the excited state just decays really fast and doesn't stick around long enough to do something interesting? Kind of like this part of this window, which is really, really hard to constrain. And I want to talk briefly about astrophysical scattering. Okay, so in this case, if your mass splitting is kind of below the sort of kinematic threshold for particles moving around in the halo, you could potentially upscatter and downscatter in interesting ways. So here I'm showing a process where you have exothermic scattering. You take two excited state particles, you scatter them, and you make a ground state particle. And to conserve energy, those ground state particles, again, are getting a pretty big velocity kick. Or conversely, you can upscatter in an endothermic process. And so we wanted to understand a little bit about what would happen. And a few years ago, we ran some simulations, just trying to be as extreme as possible and say, well, this is like something that no one has ever simulated. So let's just see what happens if we start the simulations with just 100% of dark matter in the excited state, and we have a collisionally downscatter. And what does it do? No surprise, it puffs up the halos, because essentially what happens is you give them a little velocity kick and they become gravitationally unbound. So here's the distribution of energies, okay? And we can see that for both CDM and elastic scattering, they have slightly different distributions of energies, but qualitatively they're pretty similar to each other. Whereas for the inelastic case, you have this peak over here, which corresponds to the velocity kick that you get from this mass splitting, delta, okay? And these guys are gravitationally unbound. And what that does for you is it actually really reduces your central density, because you've kicked out these particles and you've made the gravitational potential shallower, which makes it more susceptible to stripping and so on, okay? And one thing I want to emphasize about this is that we were just doing this just to kind of like tinker with it and see what would happen. We were working in this light mediator regime where you get this interesting Sommerfeld enhancement. We didn't know at the time about this other thermal history that I told you, where you can actually have this resonant behavior. Okay, so there could be some interesting thing to look at there, but we haven't done simulations in that regime. But what I do want to say is that, sorry, I know I'm over time, but Stephanie ran these great simulations where these are in the Born regime of scattering, and the couplings that we chose here were motivated by Friesen. So we chose the couplings specifically to match the Friesen couplings. So for the experts in the audience, we chose the dark gauge coupling. So we chose alpha dark to be like around 0.1. That naturally forces the dark photon kinetic mixing to be quite small. So you're consistent with all your constraints on dark photons. And something that you can see in that thermal history is, again, if you have all your particles in the ground state, because for the Friesen case, you can have a really short lifetime for decay to the ground state, you can actually still also make a difference. So these are the simulations that we did with this endothermic scattering channel. This was exothermic only, and this was CDM. And you can see by eye there is a qualitative difference. The ones with endothermic scattering are a lot more concentrated. And this really also changes if you look at different parts in cosmic history. So because you have this natural sort of kinematic barrier to upscattering, like you have a natural velocity threshold, then at high redshift, okay, over here, CDM, which is the top, and the endothermic scattering case look very, very similar to each other, because your halos haven't grown quite enough yet to be to the size that they would need to be, where the typical velocities are above that velocity threshold. Okay, so at early times, they look kind of similar, but as time goes on and your galaxies merge and accrete and they get bigger and bigger, now the typical velocities go up, And so now you can actually have a lot of upscattering. And at the end, at redshift 0, the two look quite different. So this is kind of giving you another interesting handle, the redshift dependence of this behavior. So that's very, very interesting. I'm over time now, so I just want to say the upshot is that inelastic scattering could completely change how these dwarf galaxies look, even just by eye. But one crucial caveat, the simulations I show don't have any baryons. Okay, so we heard this morning about how important that is. And I think there's a lot more work to do along those lines. And so with that, I will just summarize and say that even very, very well studied, very well motivated dark sectors, there are still these nooks and crannies of parameter space where they still haven't been fully explored. So there's still a lot of room for creativity and using complementary different types of observables. So that's where I'll stop. Thank you. Sorry for going over.